Hello to everyone, I'm Emanuelli and my project focuses on the study of disruptions and runaway electron simulations in DTT using the JOREC code. I mainly have an energy and nuclear engineering background and I have just started my second year of PhD. As a part of my first year, I spent about 4 months at IPP Garching to learn how to use the JOREC code. Nuclear fusion is a very promising technology for energy production, but so far it is still in the experimental phase. DTT is an experimental tokamak that will be built in Italy with the purpose of studying phenomena involving the divertor component, which will be crucial in the step from ITER to the European demo. In this framework, disruptions are sudden termination of the plasma that can lead to electrons of relativistic energy, namely runaway electrons. They can cause severe damage to the plasma-facing components, so it is essential to explore avoidance and mitigation techniques. The main goal of my PhD is to study disruption scenarios using the nonlinear MHD code JOREC. Thanks to it, it will be possible to model their consequences in the specific setting of DTT, developing a better understanding of the runaway electrons phenomenology and their impact on the solid walls of a tokamak. This will eventually help the design of proper avoidance and mitigation strategies for DTT. After the preliminary theoretical and practical steps, the first key result I have obtained is the successful implementation of the DTT equilibrium inside JOREC. On the left, there are the main DTT structures used in JOREC to recalculate the equilibrium in free boundary conditions, and on the right we can see that there is a satisfactory superposition of the Q profiles and the main figures of merit of the plasma. Thus, this represented a reliable starting point for the time-dependent simulations. The simulations I'm currently running involve a process called artificial thermal quench. It mimics the physics that actually occurred during a disruption, in order to arrive in a simplified way to the post-thermal quench phase. This can be done by tuning some physical parameters to match the characteristics of the desired disruption. On the right, there is the plot of a simulation of mine in which the artificial thermal quench leads to an upward vertical displacement event. To conclude, the main goal of the project is to estimate the heat loads due to runaway electrons in DTT, helping the design of components that prevent or mitigate such events. This project also has a strong synergy with external research groups, such as INEA, Consortio RFX, and the IPP. After the first preparatory steps, I am currently working on simulations of the artificial thermal quench in free boundary conditions, and the next goals will be to include the runaway electrons module of JOREC to simulate the current quench phase. 3D studies will follow to evaluate the termination of the generated runaway electron beams in DTT. Thank you all for your attention.